Hello everyone, here is Natalia Weber.
And here's Augusto Beneman, and our project is called Climate Power Forecast.
The idea behind this project is that renewable energy are directly impacted by climate change. Not only the renewable energies, but also the supply, the demand, the whole electrical system. But at the same time, the renewables are super important to mitigate climate change. So we have this paradox in which the renewable energy are directly impacted by climate change, but at the same time, extremely important to mitigate the emissions. So the idea here is to fine-tune how much renewable energy can we plan and produce, considering the new weather patterns that is going to change with the new climate that we have, because in this new climate we are having increase in ambient temperatures, we're going to have wind patterns change, and also some precipitation uncertainty. So power plants are going to be less efficient, precipitation is going to reduce in some areas, in other areas is going to increase. So how can we adapt the electricity production or the power production to these new climates?
So, before we dive into the methodology and project details, let me give you a quick tour of the website we developed. This is climatepowerforecast.com. Here you can see a map displaying the energy potential for various renewable sources. For now, since this is our initial version, we are focusing on wind energy in Latin America. But our plan is to expand globally and also include other renewable sources soon. It's easy to understand. The stronger the color, the higher the energy potential. And in doubt, you can always check the legend in the bottom left corner. Right now, you are viewing data for 2025, but over here in the sidebar, you can select any year between 1970 and 2099. You can zoom in and out, and if you want details for a specific location, just click on the map. A dialog pops up, showing the wind power for the selected year, along with a graph that includes both historical data and future projections. Well, that's it. Now let's get into the methodology behind the project.
So the methodology developed to simulate how climate is going to be in the future and how can we understand the impact on the energy production. So the method is to use climate data. Climate data is simulation of the future climate made by different institutions and organizations based on historical data, plus different scenarios of how going to be the emissions, how is going to be social development. So there's plenty of assumptions for those scenarios. Everything is developed by the IPCC. So we use those climate data that was simulated for up to 2100, and then we get the variables that they calculated, for example, the natural inflow or the wind speed, solar radiation, and temperature, and we get those variables from climate data, and we transform this data in energy potential. In this case, we use the data from the scenario RCP 8.5. So the step one is to gather the data. We use the Cordex model, which is developed by the HatGem. They have the global models with high resolution, and then they also have the regional climate models. That's the one we use. We use the regional Cordex model for Latin America, which in this case has a resolution of 44 kilometers. And we use the historic period from 1971 up to 25. And then from 2006 to up to 2099 is the future projections. We chose the scenario 8.5, which is considered a very high projection. Here's an interesting graphic which shows how much was the historical temperatures and what different scenarios are projecting. So the 8.5 is going to have up to 4 degrees more by the end of the century. This RCP 8.5 can be something in between here in the future, but it's limited to 4 degrees by the end of the century. Right now we are already around 1.1 degrees Celsius warmer than the historical values, than pre-industrial values. And this is also interesting to see how it's going to be the impact on different generations. And what is interesting about the RCP 8.5 is that actually it's where are we heading now if we don't do anything? So we keep doing exactly what we are doing now, we are going to reach the RSP 8.5, which is the very high. Here is just a more simplified version of the scenarios. So the medium scenario, the intermediate scenario, it's called RSP 4.5, which considers that we have declining on the emissions by 2045, which is in 20 years from now. We really start to decline the emissions, so then we could reach 2.5 degrees by the end of the century. But if we continue doing what we are doing, which is basically nothing, by the end of the century we are going to be up to 4 degrees Celsius. Of course, there's other different scenarios. We chose now where are we heading to. Now I want to explain to you the second part of this methodology, which is to calculate the wind energy potential, or how much energy is going to be able to produce with the future wind patterns. So first we get the wind speed data from the Cordex model, and we need to transform this data. So we choose a methodology which it's a more simplified version, in which we select a wind turbine, and then we can have already how this wind turbine is performing. For example, how much is the power output of this wind turbine, and what is the wind speed that this turbine is working. And then the second step is to extrapolate the wind speed on the near surface, which is 10 meters, and you need to extrapolate to the hub height, which is 100 meters. The third step is to calculate the power curve. And then finally, we calculate the energy output, which is basically the power calculated in the third step, plus 3, because in this case the climate data from the Cordex model, it is in 3-hour intervals. So the power is calculated, and then we need to multiply by 3, which are the 3 hours. Then we have the values in kilowatts hour. So how the wind power is calculated? So to estimate the power output, we have this different wind speed range that the energy is produced. For example, the start speed is from 0 to 10 meters per second. So in this range, you have a lower power production, but you can see that you have a steep curve. And then from 12 to 25 meters per second is the power zone, where is the wind turbine is producing at this full rate, which is in this case 2 megawatts. And then if it is too windy, normally more than 25 meters per second, it's when the wind turbine needs to be shut down for safety reasons. And this method has some limitations, which is important to point out. So this method has simplified assumptions that the standard power curve assumes ideal conditions and also constant air density, no turbulence, and perfect turbine performance, which may not reflect real-world variability. For example, we have different air densities for onshore wind production and also offshore wind productions. Also, the temporal resolution, so using these 3-hour wind data can also have some distortion in the power estimates due to the non-linear relation between the wind speed and power. And then finally, as we are doing projections up to 2099, so we are assuming that the technology is going to remain the same, which probably is not the same, that we hope that in future is going to have a more efficient, larger or optimized wind turbines that is going to be able to have an even better power output. But we are considering, and future developments we would like to incorporate in this platform we developed is to also estimate the future solar energy production using also data from Cordex, but incorporated the losses due to change in temperature, because for every degree Celsius, solar power plants, they can reduce 5% of its efficiency. And here is an example of how this data can be used for the energy planning of a region. This is the case that was done for Brazil. So with this data, you can track how much the wind power production is going to change for different regions and for different scenarios, and also different energy sources. For example, for RSP 8.5, you can see that in some regions the hydropower production is decreasing, in other regions is decreasing, and here is increasing. For example, the wind power in some regions are not changing at all, and in other regions are decreasing. So that's the goal, that we can have those data available to support energy policy decisions or even technical developments, that you can see in the future which regions are going to be better to install new power plants, or what is going to be the impact in the overall energy production of a country or region. Thank you for watching us up to now. So it was a pleasure to be part of this course and to meet James and Jason. Here is my contact. It would be a pleasure to keep in touch with you. Thank you.